So elastic collisions. These are collisions where there are two objects. So let's just call this object A and this is object B. So before the collision, what happens is object A and object B are going toward each other. So object A has a positive velocity and object B has a negative velocity going left. And then after the collision, what happens is, so this is object B, this is object A, they bounced off of each other. So object B after the collision has a positive velocity and object A after the collision has a negative velocity. So the only equations that you need to remember for this is there's two equations. So the first thing that you need to remember is that inelastic collisions, with elastic collisions, energy is conserved, kinetic energy is conserved. So let's just say K before is equal to K after. So kinetic energy is conserved. None is lost. So think of like a rubber band. Elastic collisions, if you stretch it, it's going to return right back where it was to begin with. So it's elastic and energy was conserved. So again, the object bounce apart in elastic collisions. Let's see. So the two equations that you need to remember for this, the first one is that momentum is conserved. So the first thing that you want to remember is that P, let's see, PA1 and PB1, so PA1 plus PB1, we're going to make this equal to PA2 plus PB2. And notice these are momentum. Momentum is equal to mass times velocity. And momentum is a vector because velocity is a vector. So like if velocity is negative, then momentum is going to be negative. So we can expand this out to form a bigger equation that makes a little more sense with this particular scenario where they bounce off. So at first, velocities are going like that, and afterward they're going like that. So what you can do is you can do MA, so the mass of A times VA1, and we'll keep that as a vector, plus MB VB1. I'll keep that as a vector as well. I'll make this equal to MA VA2, keep that as a vector, plus MB VB2. Yep, so I'll keep those as vectors. But now what we can realize is that here, for box B in the before scenario, velocity is negative because it's going left. And you can just decide that. It's just the easiest way to decide, oh, left is negative, right is positive. You could make it the opposite, but it would make it tricky to think about. A, the velocity is going to be positive. Afterward, the B velocity is going to be positive, and the A velocity is going to be negative because A is going left, B is going right. So what we can do is rearrange this equation to fit that. So these velocities are vectors, which means like they can have a direction, so they can be negative or positive. So what we can see is that everything is positive right now, so it doesn't really fit the scenario. but let's make it fit the scenario. So before v is negative, so in the b, for b. So we'll just do this. We'll put a minus sign here, mb, and we can actually take away the vector vb1, that's vb1. Let me write that again. Alright, so I took away the vector because I made it negative. And so mass A, B, A1. I took away the vector because it's positive and it doesn't affect this term. So now I'm going to do equals. So afterward, so just to note, all of this is before, and then all of this is after. And that continues down. So this is before, this is after. So afterward, let's see, let's see. So is velocity A negative? Yes. Afterwards, it's going to negative ma ba2 plus mb vb2, because velocity 2 is positive. So this is the first equation that you can use, and it's kind of hard to remember this, so it's a lot easier to just use this, because this is true with elastic collisions, like no matter what. So what you can do is, like, once you know your situation, then you can expand it and get this equation, which is more useful to you. But this one's easy to remember, so just remember that one. So remember that one. And then the other equation is just, it's this. So let's see here. So all you have to remember for like the next one is that the difference in approaching velocities is equal to the negative difference of velocities when they go away. So the difference in velocities here is equal to the negative of the difference of velocities there. So the difference of velocities here, so let's see what that would be. So that would be VB1 minus VA1. So VB1 minus VA1, that's the difference in velocities. And these are vectors, is equal to the negative of the difference in velocities as they go away. So this would be VB2 minus VA2. And notice these are still vectors, so like here VB1 is negative, right? So it would be actually negative, and you can adjust it that way. But yeah, this is another equation that you can remember to solve the elastic collisions. So yeah, that's elastic collision. All right, so in elastic collisions, what these are is, it's something like this. So this is before the collision. So there's two things, object A and object B. They're moving toward each other with some velocity. They could be like, this could have a not have a velocity, or this could not have a velocity, in which case you just make the velocity 0 and it would simplify the problem. But we're just going to talk about it as if they both have a velocity. And then after the collision, what you're going to have is object A and object B like connected to each other. And then they're both moving this direction or the other direction depending on whatever happens. But the important thing with inelastic collisions is they move together. So it's actually completely inelastic collisions where they move together. There's also inelastic collisions, incomplete inelastic collisions, where they don't move together afterward, but we don't really have to know that right now. So inelastic, we're just going to be doing completely inelastic, so they're moving together. So same thing happens as with the elastic collisions. So what we're going to do is P before, so the momentum before is equal to the momentum after. So the momentum before the collision is equal to the momentum after the collision. So momentum is conserved. Momentum is conserved in both elastic and inelastic collisions. The only difference between elastic and inelastic is inelastic collisions do lose kinetic energy, whereas elastic collisions do not lose kinetic energy. Energy is conserved in elastic collisions. So when they're moving, when they bounce, energy is conserved, and that's elastic. When they go together, energy is not conserved. Because some energy is lost due to the collision, like in the form of sound or in the form of heat or something like that. So what we can do is, like, since P before is equal to P after, so momentum is conserved, what you can do is so there's a couple equations we're going to look at. So P equals mv, and we're also going to do kinetic energy, so 1/2 mv squared. So actually the vector doesn't matter here because it's going to be squared anyway, so direction doesn't matter. So we're just going to leave k as 1/2 mv squared. So what we can do now is we can expand this. So before, we're going to do the mass of A. Make sure you can see this. The mass of A times V A1. So when I say 1, I'm just talking about before, and when I say after, I'm talking about 2. And so what we're going to do is add that. So P before, so this is all the momentum before. We're just going to do that. And I'm not going to worry about signs or anything. So MB V B1 is equal to, so P after. So P before, this is P before. I'm going to make it equal to the P after. So I'm going to make it to the momentum afterward. So this is MA V A2 plus MBVB2. So now we're going to adjust for the signs. So in this particular completely inelastic collision, afterward they're moving this direction, and before they're moving together. So this velocity is going to be positive. I'm referring to this here. This velocity is going to be negative, and then this velocity is going to be positive, because I'm taking right to be positive and left to be negative. So what we're going to do is P before is going to be MA plus VA1, because that's moving right, so V just becomes positive. But here, this is going to be MB. So what we'll do is we'll move the negative to here. Negative MB VB1, because velocity here is negative because it's moving left, so we're going to make that negative, because this whole thing will be negative because that is a vector. It's going to become negative, and the negative moves there, and then this is not a vector anymore. So now we're going to have MA VA2. So VA2. So what you can notice actually is that here their velocities are different, right? Or even if they were the same, they're two different velocities that you're looking at. In the after scenario though, since they're connected together, their velocities must be the same. So we can just call it one velocity. So we can just call it V2 plus MBV2. So these are actually the exact same term here, the same variable. So now what we can look at is, since those are both positive, they're just going to be added together. So then this now becomes V2. We're going to factor out the V2, MA plus MB. And you could leave it like that, but I'm just going to simplify a little bit. Because say that they ask you to find like V2, you can solve for it this way. So okay. So now you would just divide both sides by this, and then you'd be able to solve for V2. Another thing that you'd want to consider, so that's conservation of momentum. It applies for elastic and inelastic collisions. We're going to be talking about, since it's inelastic, the kinetic energy, it's going to be different afterward than it was before. So what we'll do is we'll do K before, and then we'll calculate K after. And what we'll do is we'll just compare them, and we can find the difference between them. So remember, K is kinetic energy. So what we can do is, again, the equation for kinetic energy is 1/2 mv squared. So 1/2 ma. So we're finding the kinetic energy before, so we're looking at this right here, this little collision, or this situation. So K, ma, okay, V is going to be just VA1 squared plus 1/2 MB, and we'll actually do it negative, because the velocity, well, it doesn't matter, so it can't be negative, because the velocity is going to be squared, so it's going to be positive anyway. So MB, and then we'll do VB1 squared. Okay, so that'll be the kinetic energy before, and then the kinetic energy afterward is going to be, so it's going to be, let's see here, 1/2. So now we can think of this as one object. Let's just think of it as one object. So we'll just add the masses. So MA plus MB. So I'm just replacing M with MA plus MB because they're connected together. And then we'll just call this V2 squared. And that V2 is what we found previously. That's the V2. So what we can do is, now that we have the kinetic energy after and the kinetic energy before, well, if we do K after minus K before, that'll give us the difference in kinetic energy. So yeah, and that's completely inelastic collisions. That's all you'll have to know.